Today we discuss one important topics related to eigenvalue and eigenvector. Okay. In previous class we also discussed this one, eigenvector and eigenvalue and definition of this. Today we start from one theorem. We write the statement of this theorem. Now here let A belongs to M n cross n if, then what happened? Then a scalar lambda is an eigenvalue of A if and only date of A minus lambda in equal to 0. Okay, we're now going to be proof of that. Okay, so we write this proof now. Here is scalar lambda is an eigenvalue okay, of matrix A. Here a scalar lambda is an eigenvalue of A. Then what happened? Then if and only if, okay, there exists a non-zero vector. Vector V belongs to Fn such that AV equal to lambda V. Okay, AV equal to lambda V. Understood? Then what happened? That is what? That is here A minus lambda in V equal to 0. Okay, then what happened? That means also write some, that means from some theorem. This one is not invertible. Okay, if and only if A minus lambda in, okay, is not invertible. Okay, then what happened? Then this one is not invertible. Okay, then date of this equal to 0. Okay, so this one is not invertible, means this rank is less than n, and obviously then date of this equal to 0. Okay, here that means rank of this matrix is less than n. Okay, and then this one is happen, not a problem at all. And obviously this one that means we find this one by this definition of eigenvector or eigenvalue. Okay, that means this one is eigenvector sum V, then this satisfied, and then this one is done. So easily we get this theorem. We prove this theorem also easily. That means a scalar lambda is an eigenvalue of if and only if this one equal to 0. Okay, date of a minus lambda eigen equal to 0. So now it is that portion and going to further discussion of that. Okay, let a belongs to m n cross n a. Okay, the polynomial ft equal to date of a minus tin, okay, is called the characteristics polynomial of a. Okay, next we're going to discussion one important theorem related to this problem, eigenvalue and eigenvector. Okay, so we write this example here. That means we're given this matrix here 1 1 4 1. Okay, belongs to this m 2 cross 2 r. Okay, then what happened? We also write its characteristics polynomial a minus lambda 2 date. Okay, 1 minus lambda, yeah, 1 4 1 minus lambda equal to what? Here lambda square minus 2 lambda plus 1 minus 4, that means minus 3. Okay, then what happened? Lambda minus 3, lambda plus 1. Then what happened? The eigenvalues of a are the eigenvalues of a are 3 minus 1. Okay, so not a problem at all. We also write this characteristics polynomial, and obviously we find that means this one be the characteristics polynomial, and obviously this one are eigenvalue. Okay, so that means we also further proceed. We just write one theorem related to this problem. Okay, so we erase that portion and going to further discussion of that. So we write this theorem, just statement of this theorem. Let A belongs to M n cross n A. Okay. Then what happened? Here the characteristics polynomial of A, the characteristics polynomial of A is a polynomial of degree n, is a polynomial of degree n with leading coefficient -1 whole to the power n. Okay, the characteristic polynomial of A is a polynomial of degree n with leading coefficient, this one. Okay, next, A has at most n distinct eigenvalues, n distinct eigenvalues. Okay, so the characteristics polynomial of A is a polynomial of degree n with leading coefficient, this one. Okay, and obviously A has at most n distinct eigenvalues. Just we write this theorem. Okay, not we write this proof also. Okay, that means some date of the characteristics polynomial means date of A minus lambda n. Okay, this one obviously that means some in this way -1 whole to the power n, x to the power n, and dot dot dot. So this one is leading coefficient, where that means x n degree n, polynomial of degree n with leading coefficient, this one. And that means we elaborate this one, and this one we get. And obviously this one is in, that means degree n polynomial, the degree n, a polynomial of degree n. So obviously it gives at most n distinct root. So n distinct root, this one equal to 0, we get n distinct root, and n distinct root is obviously eigenvalues, and otherwise less than n distinct root. Okay, so not a problem at all. This one is easily get from here. Just we write the statement of this theorem. Again, we're also going to further discussion of that. That means another theorem related to this topics. Okay, so we erase that portion and going to further discussion of that. Okay, let T be a linear operator on a vector space V and lambda be an eigenvalue of T. A vector V belongs to V is an eigenvector of T corresponding to lambda if and only if V not equal to 0 and V belongs to this one, nullity of T minus lambda I. Okay, so I think this one is not a problem at all. That means just write this one equal to here T minus lambda I V equal to 0. Okay, this and obviously this one from definition this one is obtained. Okay, not a problem at all. If vector is an eigenvector, then this one this represent TV equal to lambda V. Okay, that means that gives this gives this gives this, just another representation of definition, so not a problem at all. So we from and that means by definition we get this one. Okay, so today we discuss just eigenvalue problem, some theorem. We also prove this theorem. That means I lambda is an eigenvalue of A, then date of A minus lambda I n equal to 0. And we give one small example and another theorem, another two theorem. Okay, so today I stop here. I think all are understand this topics easily. So today I stop here. If you get this type of video, please subscribe and follow my channel and click on like options. Okay, so today I stop here.